Hello, welcome to Lecture 11. Before we begin this lecture, I just want to do a quick recap of what we did last time. Last time we looked at the electric fields due to continuous charge distribution. What we did was we broke our object, in this case a ring, into little pieces of charge, and each little piece of charge was called an element of charge, and it had a symbol of dq. Each little piece of charge dq made a little element of electric field dE, and we found the total electric field by doing the sum of all those little bits of electric field. In the case where we do a sum of many, many small pieces, that sum is found by doing an integral. So using that method, we were able to find the total electric field due to a ring of charge, where the charge was uniformly distributed. We're going to be using that idea some more, so I thought a recap was in order.
It turns out that knowing the electric field around a plane of charge can be very useful. So let's define what we mean by a plane or a plane of charge. So first of all, we're talking about an infinitely charged plane. Our plane, we'll say, lies in the xz plane, and it's very thin in the y direction. So infinite in x and z, thin in y. So this dimension is very small. Sometimes we just call this a thin plane. For a charged plane, we assume that our plane has a uniform charge density or a uniform charge distribution, which means if you take your plane as having positive charges, all of those positive charges are evenly spread out. So they're all equal distance apart. For our charge density, we define that with the Greek letter sigma, and that's equal to the total charge divided by the total area. That has units of coulombs per meters squared. Well, we know that electric field, if we're trying to find our result for electric field, we know that that points out from a positive charge. It turns out that the total electric field of a plane is constant, and it's perpendicular to the plane. So if we were to draw the electric field anywhere, it would just point straight up. That's kind of an interesting result. The electric field has a y component, but no x or z components. And it turns out that the size of the electric field doesn't matter how far away from the plane you are. We can certainly find this result by doing an integral. It's outlined in your textbook if you're interested. If you love your Math 1001 class, you might like to go through the process, but I'm not going to ask you to reproduce it. In a nutshell, the method is that you take the electric field of a ring and use that result to find the electric field of a solid disk. Then you let the radius of the disk go to infinity, and that becomes an infinite plane. We are also going to find the result for the electric field using Gauss's law in the next chapter, and we'll see that that's a pretty easy process to do, but we won't get ahead of ourselves. Let's get an idea of how that electric field result comes about and what the electric field is. So let's switch to an edge-on view of the plane. Let's say we have our positive charges in the plane. To find the total electric field, we have to find the electric field due to every little positive charge and add them up. That's the process of doing the integral. But as an illustration, I'm just going to draw the electric field of 3 of these charges to give us an idea of why it's straight out and perpendicular to the plane. So our left charge makes an electric field that points up and right. Our right charge makes an electric field that points up and left. And our middle charge makes an electric field that points straight up. So if we consider all of the charges, if we added up all of the x components, they would all go to 0. Let's just get our coordinate system on here again. So z is coming out of the page towards us, x is left and right as y is up and down. All of the z components would also cancel, and we'd only be left with the y components. They wouldn't be 0. And it turns out that those y components would actually, after you do the sum, would be all constant. Let's flip over onto the next slide to see if we can examine why that would be constant. To illustrate that again, let's look at a bunch of charges. This time I drew more than 3. I'll label them each as positive. Of course, you can find this result for a negative plane too, but I'll start with positive. So let's pick a point right here and let's find the electric field at this distance. Well, what we know is that each of those charges has an electric field that points away. They're a little bit hard to draw very well, but I'll give it my best shot. The one from directly underneath points straight up. Then there's symmetric on the other side. I'm drawing this freehand, so it's hard to get it exactly symmetric. Hopefully you get the idea. Okay, those are the electric field vectors for the whole place. We see that all of the EXs and the EZs go to 0, and the EYs add up. And of course, when we're doing the integral, that means we would do the integral of each little bit, but it's okay just to say they add up. Now, the fact that our electric field is constant a distance away, let's pick a point that's further away and draw those electric field vectors. So the one from the middle points straight up. Now, this electric field vector is smaller because it's further away, but the next guy over, see how that angle is steeper than it was on the bottom? Okay, my drawing is really going downhill fast here. I invite you to grab a ruler and draw these for yourself if you wish. And this was something I did years and years ago, was I didn't believe the electric field was constant, so I did this exact process, and I did manage to prove it to myself that it was constant. So as we get further away, E itself, the magnitude of the electric field, gets smaller, but the Y portion of every contribution gets bigger. So you get a bigger and bigger fraction of your electric field that's a Y component, and they add up. And the overall result is that the electric field is constant. That's a pretty neat result. So let's finish by writing down what the result is for the electric field around a plane. So the electric field has a magnitude of the charge density sigma divided by 2 times the permittivity of free space. So epsilon naught is the permittivity of free space. That has a value of 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. Electric field, of course, is a vector, so it points away from a positively charged plane, and it points towards a negatively charged plane. Now, if you're looking for a nice picture of the electric field around our infinitely charged plane, I nabbed one from a book and popped it up on this slide, and I wrote the equation down here too. Again, we are going to find this result using Gauss's law in the next chapter, but for now, I'll just present the result and we'll use it moving forward in our examples.